Hello and welcome to another exciting video here in Mathland. We are still in section 9.6 and this is permutations. Yay, pretty cool word, huh? Yeah, it's exciting here, the world of probability and statistics. Okay, so permutation, we've kind of seen stuff like permutations in the last video and ordering stuff, but this is kind of specific. So we've kind of dabbled in this, a little bit here, a little bit there, with the last video and the last set of homework problems, but now this is very specific to an order of elements here. So it says the definition of permutation, a permutation of n different elements, is an ordering of the elements such that one element is first, second, and third. So the order of it matters. So if you had, if you're in a race and you can only have one winner, right? And one second place finisher and one third place finisher. So the order matters in permutation. So if you have three designated jobs and you want to elect a candidate for them, that you can't have one person doing two jobs, or you can't mix them around. So if you have one person president, one person vice president, and one person secretary, that order matters. So where you put which one. So let's take a look at some examples here as far as permutations and orders. So we've got find the number of permutations of n elements. It says how many permutations are possible for the letters A, B, C, D, E, and F. Okay, so consider the following reasons. So the first position, second position, third, fourth, fifth, sixth position. Okay, so this is kind of what we did with the phone numbers, and we did other stuff with this kind of option. I think the last example, in the last video, showed us that we could have different kinds of digit selecting. So this is kind of the same thing. So we have the letters A, B, C, D, E, and F. Okay, so we have positions here. We have one position, 2, 3, 4, 5, 6 positions. So I like to put little dashes here to figure out what can be in each position. So how many can I choose from in the first position? I can choose all 6, right? But I can't choose 6 for the next one. So in permutations, you have taken one out. The order matters here. So if I took 8 out, how many do I have left? Well, I have 5 left, and 4 left, and 3 left, and 2, and 1. So we have a similar kind of counting principle that we saw in the last video, only this also looks like a factorial, right? 6, or 6 factorial. And this is the amount of permutations we will have. So let's figure out what that is. 6 times 5 times 4, or we can just use that cool thing, that cool feature on our calculator, the probability. I mean, who doesn't love using their calculator, especially when we have probability and exclamation marks, right? Okay, I gotta put my 6 in there first. 6, math, and probability. I could figure it out in my head a lot faster than I'm doing this, but it's more fun this way. So 720. There are 700 possibilities with this. So once you take a letter, it's gone. Okay, so it's gonna involve these factorials. Okay, so then they have this cool little formula down here, which you can use totally on your own. I'm not gonna go too much into it because I'm going to let you use your calculator for permutations, and there is a calculator button for this. And we're going to figure out what that is on the next page. Okay, so this is the factorial thing. We know about that. What about this one up here? So we have counting horse race finishes. Okay, so we have a first, second, third, and apparently in horse racing you call it a win, a place, and a show. Okay, so all you people out there, high class, knowing what horse race placement is, that's great. Okay, so it says 8 horses are running a race. So we have how many different ways can these horses come in first, second, and third? So we have 3 options here, right? First, second, and third. Okay, first, second, and third. All right, that was it. And we have how many to choose from? We have 8. 1, 2, 3, 4, 5, 6, 7, 8. You don't have to write those out. I'm just putting it there as a visual reminder of how many we have to have. Okay, so in our first position, okay, if somebody comes in first, we have an option to choose from. We have 8 numbers here, right? 1, 2, 3, 4, 5, 6, 7, 8. 8 options to choose from. Now, if I take that one away, how many more do we have? We have 7, and then we have 6 for third. Okay, so you could do the factorial here, but then you'd have to divide by another factorial to eliminate all this stuff. So let's go ahead and multiply these out. I'm not going to use the factorial because it doesn't go all the way down to 1. we have a truncated version of factorials. So we're just going to multiply 8 times 7 times 6, which is 336. Okay, so now with these non-complete factorials, we have a formula coming up here for permutations. Ta-da! There it is. Okay, so here we have our n value, which up here was our 8. So we have 8 factorial, our n value there. And then below it, we are going to have to cut it off at some point, right? So where did we cut it off? We cut it off at 5, right? So anything below 6 was cut off. So we have 8 minus our r is 5. It's 5. So we're going to cut that off at 5 and then exclamation point. Okay, so then you can see, oh, look, they have it right here for us. So we can put that into the calculator as 8p instead of c. We haven't seen this one before. 8p 3. Ta-da! So we have 8 over, oh, sorry, this should have been a 3. I was thinking we cut off the 3. Okay, so it should be 8 factorial, 8 minus 3. We have 3 places. Sorry, 3 places, and this is what we started with. Starting value. Okay, there we go. Does that make more sense? There we go. Oops. It's just like we're here together in the classroom where I make mistakes and you just go along with it. Okay, so we have 8 minus 3, that's going to be 5. So we have 8 factorial over 5 factorial. Okay, so this is what happens here, and this is what that looks like as far as our calculator work here. Okay, so we can put this into the calculator. Let's see if we get the same thing. Okay, so if you're rocking a TI-84 plus, you can just go to math probability here and go to the NPR. How about that? Look at that. And then you can put in the little squares here. We have an 8 and we have a 3. And we get the same answer, 336. Now, if you have an older version of a TI-83 or something like that, you'd have to put in the 8 first. You have to put in that little number first, 8 math probability, NPR, boop, and then 3 here. Okay, so you get the same thing. You just have to put the first number in first instead of going straight to the math probability, NPR. Okay, so let's see what's next. Okay, we're going to jump straight over to combinations in this video as well. Okay, so combinations, we've seen this before. It's the NCR, but how are these different than permutations? Well, the combinations have kind of groups of this. How many groups of this can we come up with? So I'm going to try to make it as clear as I can between the two, but we're going to read about combinations first, and hopefully I can kind of clear the specific details of each one, permutations versus combinations, in just a little bit. Okay, so it says when you count the number of possible permutations of a set of elements, order is important. Remember, we had the first, second, third winner of the horse race, or we have specific jobs like president, vice president, secretary, stuff like that. So the order was specific, and it's important. And so it says here, as a final topic in this section, you will look at the method of selecting subsets of a larger set in which order is not important. Okay, such subsets are called combinations of n elements taken r at a time. Okay, so we've got a combination here. So take a look at this. This might clarify what's going on here. So the combination here, ABC and BAC, they are the same when we talk about combinations. So we're talking about a group of letters together. So I have this group of A, B, and C, whether it's written A, B, and C or BAC. The group is together. So think of it as you're putting it into a bag or something. You have an A, you have a B, and you have a C. Okay, so it doesn't matter how you're writing them, hence order doesn't matter. But we have that same group of letters. Okay, so that's combinations. With permutations, we had a specific order or a specific role for each digit value or each value that's involved, like the president, vice president, secretary. You have to have a person in presidency, in vice presidency, and in a secretarial position for it to make sense. So you can switch those people around in those positions and have different permutations. But in combinations, it doesn't matter. So if you have Bobby, Joe, and Mary, you always have Bobby, Joe, and Mary. Doesn't matter what position you put them in. Bobby, Joe, and Mary are all together. Okay, so combinations, it doesn't matter if you have a group of 3 or more of the same thing, it's going to be counted as one thing. Okay, so let's see. Let's move on to example 8. Hopefully this will help you out understanding these here. Okay, oops, can you see it? Yeah. In how many different ways can 3 letters be chosen from letters A, B, C, D, and E? So the order of these 3 letters is not important, but we have to make sure that if we were to put these letters in a bag, that those are the 3 letters. We cannot count that twice. So for instance, A, B, and C is in our bag now. We can't put C, B, and A. Notice that it's not listed anywhere else, C, B, and A, because we already had that combination of letters here. Okay, so it says the following subsets represent different combinations of 3 letters that can be chosen from 5 letters. Now, since we have 5 letters, we have all these other combinations. So notice that they're not repeated. These 3 letters are not repeated anywhere else in our subsets there. Okay, so now we have a formula for combinations of n elements taken at r at a time. So it looks a lot like the permutation equation, right? Boop, but it doesn't have this r factorial here. So that's the difference right here. So now when you're doing combinations here, and you saw it in the expansion of binomials, we also have an r factorial. So again, what are we doing with this selection here? So let's do this example here. We have 5 letters to choose from. So we would have the C5 or the 5C, and then how many spaces do we have, or how many letters are we choosing? We're only selecting 3 of them. So it'd be 5C3, which looks like if we expanded this out and not used our calculator, so it'd 5 factorial over 2 factorial, because it's the n minus r was 3, and then the 3 factorial there. So again, you don't have to use this formula. You can use your calculator here, as long as you know how to plug in these numbers. So the first one is going to be the amount of things that you're doing. So think of it as not your sample space, but what you're choosing from. So we had 5 letters here, A, B, C, D, and E. And then how many spaces did we have? And that's the 3 right there. So that's how you do the combinations. So let's take a look at this example here for combinations. A standard poker hand consists of 5 cards dealt from a deck of 52. How many different poker hands are possible? After the cards are dealt, the player may reorder them, and therefore order is not important. Right, there's not a first card, second card, third card. You can put them in any order you want, as long as you have them in your hands, okay? So it's like putting the letters in a bag. You have those cards regardless of how they are ordered. Okay, so let's use our calculator for this one. It's going to be a combination of things. So how many total do we have here? We have 52, right? And then how many goes in our hand? So 5 cards goes in our hand. So it consists of 5 cards. So let's put this in the calculator. Let me dig it out here. Okay, so if you've got an older calculator from a TI-83 and younger, you would put your 52 in first. So 52 math probability. Go down to NCR. Boom, there it is. And then put a 5. And so if you have a newer calculator, a TI-85, 84, you can just go to math probability, NCR, and put in those values in little squares. Okay, so 52 cards out of 5 cards in your hand, and that would be, holy moly, that's a lot. So that's a lot of combinations there. But apparently that's how many combinations you can possibly have, and that's why poker is so difficult. So our let's see, what was it? How many standard poker hands are possible? Okay, so we've got this many possible poker hands. So what is that? 2,598,960. Are we right? Oh, yeah, we are. Okay, fantastic. Okay, we can take a look at some examples here in the homework here. Let's turn the page. Okay, so I'm on page 744. I'm looking at some examples here. So I'm looking at 47, kind of like 47 that you have in your homework here. So I have, in how many ways can 6 children line up in a row? Okay, so let's see what we have here. 6 children line up in a row. Do we use permutation or a combination? Are we looking for a combination of kids? or are we looking to see how many fill a blank spot in our line? Well, it's how many can fill a blank spot in our line. So we have 6 people in a row, 1, 2, 3, 4, 5, 6. How can they line up in the row? So I'm going to write a row of 6 lines. How many options do I have for my first blank? Well, I have 6 children to choose from. And the next one, if I choose one of them, I only have 5 left over. And then 4, and then 3, and then 2, and then 1. So this is a permutation. So I'm going to put P right there. Permutation. So we can just multiply those out. It's also a factorial, okay? So you can also put 6 factorial. Okay, so let's go ahead and figure that out. If you want to do the cool way here, I like to use my calculator because it has a cool exclamation mark. I could multiply it out. Oh, didn't we already do this one? Yeah, 720. 720. So 720 different ways that children can line up in a row. Okay, let's take a look at number 49 here. It says choosing officers from a pool of 12 candidates. The offices of president, vice president, secretary, and treasurer will be filled. In how many different ways can the offices be filled? Okay, again, 49 would be a permutation because the order matters. So you've got president, you've got vice president, you've got secretary, and treasurer. So the order matters. So of the 12, you have 12 to choose from here, and then 11, 10, 9. So you can do the permutation on that one as well. Okay, so now let's look at something that might be a combination. So number 45 here, it says write all the possible selections of 2 letters that can be formed from the letters A, B, C, D, E, and F. That's kind of like the example that we looked at in the book. Okay, it says the order of the 2 letters is not important. So if it says specifically it's not important, that's going to be a combination. Combination right there. Okay, so you can do the combination of that one. Look back to that example in the book that we looked at just moments ago there. Okay, and now we have number 51. So it says forming an experimental group. In order to conduct a certain experiment, 5 students are randomly selected from a class of 20. How many different groups of 5 students are possible? So we're talking about groups of students. So again, if Bob, Mary, and Joe were in a group, we cannot include that as Mary, Bob, and Joe because it's the same group of people in them. So we would use a combination for this one. A group of people, think of the people in a bag or in a room. They're the same 3 people that are in the room. You can't just list them 3 different times and move them around. So order does not matter. It's a group of people. So combinations for that one. So hopefully I clarified the difference between the combinations and the permutations on this homework set. Let me know if you have any questions and I will help you out.